So let me mention, but not as an excuse for all what I said so far, that this is joint work with Gennadiy Averkov and Stefan Weltge from Magdeburg as well. Let's start with the setup. So, well, a little bit of notation. For a polytope P, I call xc lin the, well, linear extension complexity of the polytope. That is just the smallest possible m, such that you can obtain P as a projection of, well, R plus M intersected with an affine subspace L. That's it. And pi is an I was thinking that there is nothing else to say about this. And, well, pi is an affine projection. This you should keep in mind. So we allow additive constants there. And similarly, xcpsd I call, well, the semidefinite extension complexity. This you obtain if you write, well, as plus m instead of r plus m here. So as plus m is the cone of positive semidefinite symmetric matrices of size n by m. So this is xc of psd. And this is two functions I would like to talk about. First of all, mu lin of d. That's supposed to be the maximum linear extension complexity of any 0, 1 polytope in dimension d. That's mu lin of d. And similarly, mu psd of d is the maximum psd, or semidefinite extension complexity of any 0, 1 polytope in Rd. And then we will talk about, well, just because it's convenient for making statements about counting something, about random extension complexities. So rho lin of d should be the extension complexity, the linear extension complexity of a random 0, 1 polytope in Rd, just chosen uniformly at random. And similarly, rho psd of d, the extension complexity of a random 0, 1 polytope in Rd. So that's the functions we will have some statements about. And here is the general picture. So remember, rho is random, mu is maximum. So of course we have these relations. Rho lin is at most mu lin. That's the maximum, that's the random. Same for the PSD. And of course, rho lin is larger than or equal to rho PSD. And the same for the maximum values, of course, as well. And here's what is known about these numbers. So Thomas Rothfuss showed in 2011 that, well, the extension complexity, the linear extension complexity of a random D01 polytope is bounded from below with very high probability by 2 to the 0.49 times D. So 0.49 you can replace, of course, by every constant which is less than 1/2. And Briet, Dadush, Pokutta showed in 2013, James was mentioning this result for different reasons, that a similar statement holds for the extension complexity, the PSD extension complexity of a random 0, 1 polytope. Only thing is that the lower bound is now 2 to the 0.24 times D, or something, anything less than 1/4 in front of the D. Again, with very high probability. And these two results, they are based on this factorization theorem that James also mentioned, the linear factorization or the PSD factorization of the slack matrices. And they work by some, well, sophisticated balancing the factors. It's not so sophisticated in case of the first result, but it's a bit sophisticated in case of the second result. And what I would like to do in this talk is to give a different proof of this second result, which is completely geometric, doesn't use any factorization or algebra or something like this. Very, very easy to understand. The main purpose for our work was to get a good idea of what is going on geometrically in order maybe to be able to generalize or come up with similar results for other cones or other situations. But in order to present something that is at least a little bit new, although it's not spectacular, I would also, and in order to be a little bit constructive, because I think that would be the only constructive statement about extended formulations throughout this workshop, I will also give this upper bound here, where it's a constant times 2 to the d minus log d on this mu lin of d. So it's trivial that mu lin of d is upper bounded by 2 to the d. That's the number of vertices of the polytope. It's very easy to see that the extension complexity is bounded by this, by just writing the polytope as a projection of a simplex. And at least we can shave off this additive log d in the exponent there. And this is what I would like to start with, this upper bound on mu ln of d, and I'd like to explain to you how you come up with something like this. So for this, let's choose some value of k. We will choose k later, and we will subdivide the coordinates. So we have d coordinates into the first d minus k and the last k. And now our set x, which we would like to obtain an extension, a linear extension for the polytope for, looks like such a pattern, right? So in this matrix, the rows are indexed by, well, 0, 1 vectors of length d minus k. So the first d minus k coordinates. And the columns are indexed by the possibilities for the last k coordinates. And then every point x comes as such a point here. This is the first d minus k coordinates, and this would be the last k coordinates. Now what we do is we say that two rows are equivalent if they have the same pattern. So we find some equivalence classes in these rows, like this one, this one, this one, this one. Actually, that's it. So in this case, we have 4 equivalence classes. And now we write our set x as this union. So we take the union over all the 4 equivalence classes. YR is, well, for the rth equivalence class, the set of d minus k vectors indexing this equivalence class. And ZR is just the subset of 0, 1 to the k corresponding to the pattern of this equivalence class. So you can obviously write x in this way. Now, 2 crucial observations. For any 2 different equivalence classes, YR will be disjoint from YR prime, because this is equivalence classes. And secondly, for any 2 different equivalence classes, the corresponding patterns will not be the same by definition. So this is 2 trivial observations. Now this you can use, so I just wrote down these statements here again. Now this you can use very easily. We would like to come up with an extension for the convex hull of x. What we do is disjunctive programming. So we know that the extension complexity of the convex hull of this is bounded from above by the sum of 1 plus the extension complexities of the convex hulls of these sets here. This is well known. It's called disjunctive programming. And then we know that the extension complexity of such a Cartesian product is bounded from above by the sum of the 2 extension complexities. And then we know that the extension complexity of, say, the convex hull of this guy is bounded from above by its cardinality. So this we write down. So extension complexity of convex hull of x is bounded from above by the sum of these cardinalities plus 1. So this plus 1 comes from this disjunctive programming. And now if you look at this, if you first of all sum up these cardinalities here, all these YRs were distinct, disjoint, pairwise disjoint. And they come from 0, 1 to the d minus k. So the sum of these cardinalities will be at most 2 to the d minus k. How about these ZRs? So any pair of ZRs is at least not the same. So what you do here at most is you sum over all subsets of 0, 1 to the k and weight every subset by its cardinality. And this is bounded by 1/2 of this. And this 1/2 I use in order to, I can conveniently use in order to account for this additive constant of 1. Now you have to choose k very carefully, and what works out is log of d over 5. And then you find that this number will be at most 10 times 2 to the d minus log d. Yeah. So not very deep, but the best thing I know of to do. And it might remind you on a proof Shannon gave in, I think, 1948, showing that every Boolean function in d variables has a circuit of a similar size. Actually, this proof inspired us to do this. Okay, this is the only constructive statement in my talk, maybe in all talks about extensions today. I don't know. And let's come to the lower bound on the semi-definite extension complexity of a random 0, 1 polytope. So here's the strategy of the proof. So let's recall. So the extension complexity, the PSD extension complexity of a polytope P, the smallest possible m such that you can write P as an affine image of S plus m intersected with an affine subspace L. So what do we do in order to bound the number of 0, 1 polytopes P for which this is possible? Well, first of all, you observe that it's enough to consider bounded extensions. So you can safely assume that this spectrahedron here is a bounded set. This is not hard to see. But it depends, at least the only proof we know, it depends on that P is a polytope. We need that it's finitely generated by its vertices. So it's not so easy to generalize this to other sets, I think. But it's very easy for polytopes. Secondly, well, for technical reasons, we scale down the 0, 1 polytopes such that they go to the Euclidean unit ball. That we can do. Thirdly, well, we consider one after the other, not all polytopes that have an extension of that time, but we do a subdivision according to the dimension of this spectrahedron here. So for every n-dimensional extension of size m, we consider all p's that we can obtain, and we will see that it's not very many that we can obtain. But there is not many choices for n. N is certainly bounded by m squared, so doing it separately for every dimension doesn't change anything in the counting argument. So this is done, so there's these 3 check marks. Now there is the crucial things which are left. So the first thing we do is, for any polytope in the set we consider, actually at this moment it's not important that it's a scale 0, 1 polytope. For every polytope inside the Euclidean ball with an n-dimensional extension of size m, we show that it has an n-dimensional extension of size m of a very special type. Very special type means, well, it is parameterized by a vector v of parameters. It's capital N parameters, bounded from above by m to the 4, and the parameter vector sits inside a unit ball according to a specific norm that we will see later. And then the setup will be done in such a way that whenever you have 2 polytopes P and P prime, P in this sense is represented by parameter vector V, P prime is represented by parameter vector V prime, then what you can do is you can lower bound the distance according to this norm that we will talk about between the 2 parameter vectors. You can lower bound by, well, 1 over n to the 3, n is the dimension of the parameter vectors, times the Hausdorff distance of the 2 polytopes P and P prime you started with. And this is nice because the Hausdorff distance now, in the case of our 0, 1 polytopes, for 0, 1 polytopes, the minimal Hausdorff distance between any 2 will be 1 over square root of d. Now we scaled by 1 over square root of d, so we will at least have a separation of 1 over d. So this is at least 1 over d. D is less than capital N, so we are safe to write greater than or equal to n to the minus 4. But what do we have now? Well, we have that all polytopes, all 0, 1 polytopes, we can represent in this way, n-dimensional extension of size m. All these polytopes, they have representations, or their extensions have representations, which, well, are pairwise far away from each other. So each of these representations has a ball of radius 1/2 times n to the minus 4 around it, such that this ball doesn't touch any other ball of the representations. So not many balls of radius 1/2 times n to the minus 4 fit into this unit ball. Now you do this volume calculation. You have a factor of 2 in front of this to be safe, because these balls around the representations might stick out a little bit of the unit ball. Certainly the factor of 2 accounts for this. If you now do this volume comparison, you find that you cannot have more polytopes having an n-dimensional extension of size m than 4 times capital N to the 4 to the n. And as n is less than or equal to n to the 4, you find that this is bounded by 2 to the O of m4 log m. And now if you, well, compare this to the number of 0, 1 polytopes that you have in total, 2 to the d, you find that the probability that a random 0, 1 polytope has extension complexity m, as I said, so it's just an additional factor of m squared if you look at the dimensions separately, so it disappears completely in the exponent here. So you find that the probability will be bounded by this. And now if you choose m small enough means, for example, m is at most 2 to the something which is less than 1/4, for example, 0.24 times d, then this will be doubly exponentially small. So this is how it goes. So the crucial thing to tell you now is how we represent what is this EV, what is this parameter space. But before I do this, let me mention, well, so what we do here is not specific to 0, 1 polytopes at all. So actually what we do and what we prove is the size of any class of polytopes inside the unit ball, which have semi-definite extension complexity at most m and have a Hausdorff separation, Hausdorff distance, pairwise Hausdorff distance of at least some parameter delta, is bounded from above by a number like this. So this doesn't have to do with 0, 1 polytopes at all, what we do here. So let's be a bit more precise about this parameter space. So the parameter space will be this VMND. So M is the size of this, the PSD matrices, N is the dimension of the spectrahedron, D is the dimension of the polytope I'd like to represent. And the parameter space will consist of, well, symmetric M by M matrices, n of them, and D times N matrix and T and a vector U. These make the projection. And these are the parameters describing the spectrahedron. And, well, the extension we are talking about, defined by such a parameter vector here, would be this one. So all x and Rn, so that identity matrix minus is convenient here, but doesn't make a difference, 1 minus some xi, ai is positive semi-definite. This is the extension we're talking about, and the projection represented by this vector would be tx plus u, of course. So these a1 up to an are meant to parameterize this affine subspace L in this way, with this fixed point where we attach the affine subspace. And, well, a1 up to an are the basis of the corresponding linear space. So this is the extension we are talking about. And now we look at a subset of these extensions, which we call the star extensions, so we call it V star. And these are those extensions with the property that this QV contains the L2 ball and is contained in n times the L2 ball. And if I apply the projection to this, then I end up in the Euclidean ball in the image space. So like this is why we scaled down the 1 polytope. So whenever an extension satisfies these three properties, I call it a star extension. Or more precise, I call this vector a star vector. And what we will see later is that every 0, 1 polytope which has an n-dimensional extension of size m has an extension which is represented in this way. Before doing this, let's look at these two lemmas which we have to prove, because I said we can represent by a vector in a ball according to a norm. Oh, I forgot to tell you about the norm. Here's the norm. So the norm in this parameter space is just the maximum of these norms. So this is the operator norms with respect to L2 metric of the A1 up to AN. The same with the projection matrix T, and this is just the Euclidean norm of this vector U. So we take the maximum of all these norms. This is the star norm. And I promised that we can represent every 0, 1 polytope after scaling it by a vector V, and by a vector V that that has bounded norm bounded by 1 according to this star norm. And what we will actually see is that we can represent it by a vector in V star, and what's easy to see is that V star is contained in the unit ball. The second thing we would like to have is this separation between the representing vectors, the parameter vectors. So what you can prove, and this doesn't have to do with 0, 1 polytopes at all, what you can easily prove is that whenever you have two parameter vectors in the star set, then the Hausdorff distance of their projections will be bounded from above by n to the cube times this star distance between the parameter vectors. So now this is a lowercase n, but lowercase n is bounded from above by capital N, so it's enough to prove this in order to have what we had on the strategy slide. So
I guess one nice thing that you get using
You don't have to discretize at all. No. You don't have to decide for a specific rounding or something of coordinates or so.
Yeah.
No.
But I mean, given the definition you're starting on, you still need to
Yeah. This is what I will show to you. Why you can represent everything in this star way, right? So this I would like to show to you, and I would rather skip the easy proofs of these lemmas. So this is the proof of the first lemma. It's just triangle inequality, nothing else. Proof of the second lemma, the same. It's also just triangle inequality and nothing else. Well, not really true. So there is this last point here. Here we use that you describe the semidefinite cone, that you can describe the semidefinite cone as it is defined. So by basically that you can describe it by linear inequalities, where the crucial thing is the coefficient vectors have norm 1, and this identity matrix evaluates with respect to these linear vectors, these linear inequalities, to the same number, namely 1 as well. So you have a set of inequalities describing the cone, where the norm of the coefficient vectors is 1, and this identity matrix evaluates to the same number 1. So this is important here. This is so far the only thing that is specific to the semidefinite cone. So, but rather jump into the third ingredient, we have to show that we can represent every semidefinite extension in a way that we require. And actually what we prove is, and this is enough to prove, whenever we have a spectrahedron which is bounded, then you can represent it. There is even an affinely isomorphic spectrahedron QV in our, the V should, okay, yes. So there is a representation QV, even it's affinely isomorphic to some QV with V in, well, VMND, and then if we represent a polytope which we scaled down to the unit ball, then you obtain from this first lemma that this V will be in V stars. So this is nothing we have to show. So crucial thing to show is whenever we have a bounded spectrahedron like this, then we can then it is affinely isomorphic even to a set like this with this sandwich property. So the Euclidean ball is contained in Q. It's contained in the n-fold of the Euclidean ball. So this is the crucial thing to prove. And this is not too hard either. So first ingredient is, well, that what's very, very handy, and I think this is somehow crucial for things like this to work, is that every face of the PSD cone is a PSD cone as well. So this is pretty special situation. Don't know how to overcome this. Why? What can we use this for? Well, we use this for assuming after, well, reducing the dimension, going to the face and doing some isomorphism and so on, we can reduce to the situation that our affine subspace L intersects the interior of the PSD cone. So it contains a positive definite matrix. We can do this by just going to the faces, which are isomorphic to smaller dimensional PSD cones. So that means the relative interior of our spectrahedron is actually the intersection of the subspace with the interior of the PSD cone. So in particular, the dimension n of our spectrahedron is exactly the dimension of the linear subspace. So this comes in very handy. What we do now is we choose a maximum volume n-dimensional ellipsoid contained in our spectrahedron. It exists because it is bounded, it's compact. And, well, this is just notation. So C should be the center of this ellipsoid. E should be the ellipsoid with this origin 0 that you translate to the center. This is just notation. And then comes in this well-known fact, whenever you have a maximum volume ellipsoid inside such a convex set here, then scaling it by n, you will have an ellipsoid that contains this set. This is nothing deep at all. Very, very simple to see. So now we establish an affine isomorphism between Rn and this L-dimensional affine subspace in such a way that 0 goes to the center C of the ellipsoid, and the unit ball in Rn goes, of course, to this ellipsoid E that we shifted from the origin to the center. And then we observe that C, because the unit ball is contained not the unit ball, well, because C is contained in the relative interior of this ellipsoid, so in the relative interior of our spectrahedron, we see that C needs to be a positive definite matrix because it's in the relative interior. It's in the relative interior because C plus the entire ellipsoid E is contained in our set. So since C is positive definite, the Cholesky factorization will have non-singular factors, and we can now use these non-singular factors to transform our situation as we want. So we define Q, that's the set we search for, to be, well, of course, the set of all x such that fx is positive semidefinite. The image of f, the image of Rn under f is exactly L. So this is exactly S plus M intersected with L. And now what we use, and this is specific to the semidefinite cone as well, of course, the semidefinite cone is invariant under multiplication with an invertible matrix from both sides. I mean, matrix and its transpose. So we can safely multiply fx with u to the minus t and u to the minus 1 from left and from right. Still will be the same set Q. And, well, now what is this function here, u to the minus 1t, fx u to the minus 1? It's an affine function, of course. Nothing has changed from Rn to L. Or at least, well, it is an affine function. It goes to L, but that's not important. So we can write it as a constant minus such a linear combination. And why can we choose this constant as the identity? This is because f of 0 is C. And if I plug in C here, because U transpose was a Cholesky factorization of C, this will turn out to be the identity. So we can write it this way. So we have arrived in the situation in the form that we like to have, and then we wanted the sandwich property of Q, and this we obtain, of course, from this sandwich property by applying the inverse of f to the minus 1. So we are all done. So nothing serious happened. Okay, so this was the proof. Let me end with some conclusions, a few problems. The bound on the norm of the AIs. This is, it enters here. V star MND has only bounded V's, so also bounded AIs. And why do I end up in V star? I just showed that I end up in V, but V star is those guys which are sandwiched and whose image lands in the Euclidean ball. These two properties being sandwiched and the image goes to the Euclidean ball, to the unit ball, these three properties, they imply that the star norm of V is at most 1. And this implies, by definition, that the operator norm of the AIs is at most 1. There's nothing going on at all, basically. So you don't need any deep structural insight.
Yeah. No, I mean, in some sense, we do exactly the same rescaling, but we're doing it in factorization.
Yeah. Yeah, I mean, you also do the sandwiching, and this is the crucial argument for bounding the spectral norm of the factors, right? Of the participants in the factors. Absolutely, absolutely. I don't claim that this proof is completely different from your proof.
No.
I just like this way of doing a proof. Might it be the same or a slightly different one? I don't know exactly, because it really reveals what the geometry of the situation is. So let me come to a few problems that are connected with this. So Well, first of all, as I said, so the basic setup does not depend on 0-1 polytopes at all. 0-1 polytopes only enter via the Hausdorff distance. So you can apply this to all classes of polytopes you're interested in. For example, you can work with polygons and obtain known results of polytopes as well. You don't get any better, but you can easily just obtain the same results with the same with this framework. Then, of course, it would be interesting to somehow get hands on other cones, but there is some subtleties, although only at very, very few places the special property of the cones arise. A bit subtle. Then, I mean, this whole business of counting what you can do with small extensions. If you restrict to extensions where the numbers you plug in are bounded somehow reasonably, so the encoding length is bounded polynomially, which would be a reasonable assumption, of course, if you want to work in practice, then counting becomes trivial. Then it's completely clear that the vast majority of 0-1 polytopes cannot have a small extension because you simply do not have enough data to distinguish the polytopes from each other. So the whole business is about, well, could it be that you can hide a complicated structure just inside the coefficients of the extension? And it would be really interesting to see some examples of hiding structure and coefficients, even if the type of extension is weird, like a co-positive or completely positive cone extension or something. How can you hide complexity of a given, concrete given problem in the coefficients of the extension? I have no good idea. Then, well, can we beat the upper bound? It's not very relevant from practical point of view, but it's a kind of intriguing question, though certainly not the most important that you could imagine. The upper bound was 2 to the d divided by d, roughly. Right? And then one question, is mu of PSD really smaller than mu ln of d? You might say that depends on d. That's true. So the first d you would like to check, d equals 2, you will already say yes. Mu PSD of d should be 3, I think, while mu ln of d should be 4, I think. But I would at least bet a beer that as soon as you go to d equals 3, why not betting a beer? They are equal. I would guess they are equal. I would guess you cannot gain anything in using SDP. Yeah. I don't think so. The maximum overall 0-1 polytopes. Yeah, yeah. I mean, certainly for individual polytopes, I think, for example, like the cube, you might. I mean, yeah, yeah. Yeah, yeah. So for there is classes of polytopes where you can separate, but I would guess that if you go overall 0-1, I could imagine. Why say guess? I could imagine that if you look at all 0-1 polytopes, it doesn't make a difference. So actually, I mean, I'm not really don't have a very good feeling for PSD extensions, but a good PSD extension of a polytope seems to be something very strange to me. I mean, a good PSD approximation of a polytope is, of course, they are ubiquitous. How do you say? They're all around. But really, exactly matching the polytope with the PSD, taking advantage of PSD to represent the polytope exactly, I can only imagine that this goes in very, very special cases. But I might be completely wrong. In any case, thanks. For d equals 2, this should be 3 and this should be 4. So because the square you can represent by a spectrahedron which has 3 variables. Oh, it depends. Oh, no. This is the dimension. The dimension is 3 of the spectrahedron. But the m is not 3. No, the m is 3 as well. So yeah. No beer from you. Okay.